So we've had our SOHCAHTOA review. We're going to need that to do our vectors. So a lot of our vectors are going to be right triangles, but sometimes they're not. Sometimes they're just going to be in a line, so you kind of have to watch that. But what is a vector? I mean, we're going to spend all this time on them. What is a vector? A vector is some sort of quantity that has a magnitude, which is how big is it, and a direction. So we're actually going to look at some examples of that real quick just so we have an idea. And that word magnitude really throws a lot of people off. So here's a couple of examples. We have a magnitude and we have a direction. 5 meters west. So the 5 meters, that is our magnitude. That's your magnitude. West is your direction. So what do you think the magnitude in the next one is? 10 centimeters. How big is it? It's 10 centimeters. Which direction is it going? It's going down. So this is 5 meters to the west. Think of the United States. We're thinking north, south, east, west. So here's the United States. Yes, I know. Looks like a cow. Okay, there's the United States. Where do we live? Here in California on the west coast. Here's New York on the east coast. So to the west is that way. Last one. Which one's our magnitude? The 50 newtons. We don't really need to know what newtons is right now. It's a force unit. To the left. Which way is left? Hey, guess what? Your left hand makes an L. So left and west are pointing in the same direction. Right and east are pointing in the same direction. We're going to talk about vectors, but what kind of quantities actually are vectors? Well, one type is velocity. Velocity is basically your speed in a certain direction. Another is displacement. How far are you from where you started? So if I start here and I go, my displacement is from where I started to where I ended. It's how far and in what direction. So generally there's an angle associated with it. How far and what direction am I from where I started? So if we looked at the compass rose, north, south, east, west, north, south, east, keeping the United States in your mind, this would be some angle, and it's pointing to the north because it's kind of going up, and to the east. So this is going northeast. So I'm northeast of where I started. Acceleration is a vector unit also. It's kind of hard to picture, an acceleration to the west or an acceleration to the east or up, down. It's easier to picture up, down because gravity, which way does gravity work? Gravity always works down, and gravity accelerates us. But an acceleration is usually a result of a force. So the force has a direction. So force is another vector quantity. And we're going to find that these two here, your force and your acceleration, are going to be in the same direction. Now, these are just what kinds of quantities. We don't have to do anything with them quite yet. We're going to deal with them more in the next couple chapters. But these are vector quantities. So velocity is our speed in a certain direction. Displacement is the distance from where we started to where we ended. Acceleration is how fast did we speed up in a certain direction. And a force is kind of like how far were we pushed in a certain, or how much were we pushed in a certain direction. So you may have noticed that when I was drawing the vectors that I was drawing arrows. And so we usually have an arrow, and the arrow points in the direction it's going. So this is either going east or it's going to the right. Okay, so it's either going east or to the right. Depends on how it was defined in the problem. But the length of the arrow is usually proportional to the size of the vector. So if I had a 5 meter vector and I had a 1 meter vector, so I had a 5 meter displacement and I had a 1 meter displacement, my 1 meter displacement would be about 1/5 as big as the 5 meter. But we represent them with arrows to show how big are they, their magnitude. Don't let that word throw you off. Their magnitude and which way are they going. And it kind of gives it a little bit more concrete rather than being, oh, you've got some going, how do I picture that? This is how you picture it. And so drawing a picture is going to be a huge, big deal in what we're doing. So say we had a situation like this. Minnie Mouse walks 5 meters north and 3 meters south. Okay, how far did she go? Well, I mean, that's pretty easy, right? She went 5 meters, then she went 3 meters. So how far did she go? 5 plus 3. She went 8 meters. Okay, so that's the total distance. If you were actually walking, you go doink, 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 and you'd count the whole path that she went. Now, what is her displacement? Now, that is a little bit more tricky question. And that's a vector idea. So what is her displacement? She went 5 meters north, and then she went 3 meters south. Notice we made the 3 meters shorter than the 5 meters. And the question asks, what is her displacement? Well, her displacement is the distance from where she started, so she started here, to where she ended. So she ended somewhere up here. Okay? So what we want to know what this distance is. This is like that segment addition stuff that you did in geometry. So 3 plus what is 5? Oh, look, she is 2 meters. Now we have to give a direction. We're going to connect where she started to where she ended. She's 2 meters north of where she started. That's basically how we would do it. Easy enough? Well, they do get more complicated, sorry. Okay, what if instead we had Minnie Mouse walking 5 meters north, so that part's the same, and then 3 meters west. So notice every time I do this, I'm drawing a picture that shows the situation. We're going to find her displacement. So her distance is still the same. She still went 8 meters, right? Because she walked along this path, and then she walked along this path, so she went 5 meters, and then 3 meters, so she still went 8 meters. But our displacement, we want to know how far is she from where she started. So here's where she started, here's where she ended, and we'll connect an arrow from where she started to where she ended. And we need to find that. That's not quite as easy, but you notice that north and west, if we did the compass rose again, that would be a right angle. So we have a right triangle here. And we know 2 of the sides of a right triangle. How can we find the third side? Think about it. Correct. You can use the Pythagorean theorem. So to find her displacement, what we would do is 5 squared plus 3 squared equals her displacement squared. You can just call it c squared. A squared plus b squared equals c squared. And so you get 25. So you find out c squared is 34. You need to take the square root of that, which often brings up a very important question. In math, your math teacher would want you to leave the answer like this. Okay, math likes exact answers, and a square root sign is an exact answer. But let's think about this. Can I really say, oh, I'm going to walk the square root of 34 meters? Does that really make sense? You need something you can measure. Physicists like things that they can measure. Scientists like things that they can measure. So we're actually going to do this math and find out what the actual answer is. So we're going to find out that our displacement is 5.83 meters. So now that's a distance I can measure. So if I wanted to, let's say Minnie and I were sitting here together, and I wanted to go join Minnie over here, instead of following her path and going here and then here, I could just walk a straight 5.83 meters in this direction. So what is that direction? There's a whole nother conundrum. Let's figure that out. So here's the drawing that we had, and here's our displacement, the 5.83 meters. Generally, we want to measure our angles from the horizontal. So we want to measure this angle here. Now that's kind of outside of our triangle, right? But remember your geometry. That's why you had to have an A in geometry, be in honors physics, but you regular physics kids should get this too. Two parallel lines cut by a transversal. Alternate interior angles are congruent. So this angle here is the same as that angle there. Okay, so to find the angle, you're going to use your trig functions. So which one do we want to use? Generally, we want to use the numbers that we were given and not round it off. We kind of rounded that number off a little bit. So from this angle, this is the opposite. So this is the opposite. And this is the adjacent. So which trig function uses opposite and adjacent? Correct. It is the tangent function. So what we're going to say is the tangent of the angle is equal to our opposite over our adjacent, which is opposite's 5, and our adjacent is 3. So we have the tangent of the angle, theta means angle, is equal to 5/3. To get rid of the tangent, we're going to take the inverse tangent of 5/3. Okay, so on your calculator, that's a second function button. And so you're going to go ahead and do that on your calculator. Go second tangent, 5 divided by 3 equals, and you should get that theta is 59 degrees. Okay, and which direction is it? Think of your, well, and we can go back to the original problem too. Do you see how Minnie went north and she went west? She went north and then she went west. So she's going to the northwest. So 59 degrees northwest of where she started is her displacement. So the whole answer you would give is 5.83 meters northwest, or north of west. Either way is fine. So here we've seen two different types of vectors. We've seen vectors that come back on themselves. They can also just straight add to each other. If I went west or east and then east again, then I would just straight add them. And we also saw vectors that were at right angles to each other, and we needed to find, this is called, it's displacement when we're talking about distances, but in general, from where you started to where you ended, this here is your resultant. So resultant is a generic vector term, and we will use it a lot. So you have the magnitude and direction of the resultant, which means how big from where you started is the resultant from beginning to the end. In the next video, we're going to do this a little bit more complicated, where we're adding vectors that are at an angle to each other. So that's really when your SOHCAHTOA is going to come into play. So pay attention. You can do this. It's not that hard. Good luck, and I will see you tomorrow. Bye.